Hi, this is Wagner Kamakura, and in this tutorial, I'm going to give you a practical and intuitive take on linear regression. Linear regression is something that is covered in most introductory data analysis or statistics class, but I'm going to build a linear regression model from scratch to give you a practical sense of what exactly does the linear regression do. And I'm going to do this from scratch just to show you how it works. And then I'm going to show you that you can run a linear regression on Excel in a much easier way. Using my Kate Kamakura analytical tools for Excel, you can even run a more complex model by selecting predictors through stepwise linear regression. And I'm going to use a data set that is right here. I'm going to use this Excel sheet that contains the data from the largest Brazilian cities with over 10,000 residents. And for each one of these cities, we have consumption of gasoline. Okay, how much was spent on gasoline in a year in each one of those cities? How much was spent on vehicle maintenance? The number of vehicles in that city and per capita income in each one of those cities. If you wanted to run the same example on your own, you can download the data from my website. I show you the URL in the bottom of the box there, but the easiest way to find it, a search on Kamakura's analytic tools for Excel, and you're going to find the link from where you can download this data. And this data, this particular sheet here, is one of the sheets in this Excel sheet called Kamakura Analytic Examples. So let me show you how I'm going to build a linear regression. So for example, is there any relationship between consumption of gasoline and expenditures in maintenance? We can look at this relationship visually here by highlighting the two columns, doing a scatter plot. And here is a scatter plot of vehicle maintenance in the vertical axis and fuel consumption on the horizontal axis. And just to make things clear, I'm going to add a title for the horizontal axis. And you can see that there is some relationship between vehicle maintenance and vehicle fuel consumption. Cities that have larger amounts spent on maintenance tend to have higher fuel consumption. So knowing vehicle maintenance would help us estimate the amount of money spent on gasoline in the city. Let's see if there is any relationship between the number of cars and fuel consumption. And I'm going to do this by changing the data on the vertical axis. So now I'm going to plot number of cars on the vertical axis. And for that, I'm going to use this column, column D. And here's the relationship between the number of cars in the vertical axis and fuel consumption. And there is clearly a relationship. Cities that have more cars tend to spend more money in gasoline, as you would expect. Is there a relationship between per capita income and fuel consumption? Let's see that. I'm going to, again, right click, select data. Now I'm going to change the vertical axis. I'm going to plot now per capita income. So the vertical axis now is going to contain column E. And there is a clear relationship again. For example, let's pick one city here to draw a line. So let's pick a city, let's say any city that has $2,000 in per capita income. Let me color this red. So any city with per capita income of $2,000 would spend somewhere between things are not perfect. There's a lot of uncertainty here. But you would say that a city that has $2,000 in per capita income would spend between 800,000 and 1.5 million reais, that's the currency in Brazil, in gasoline. The relationship between our dependent variable, fuel consumption, and each one of its predictors, vehicle maintenance, number of cars, or per capita income, can be summarized by a correlation coefficient. This correlation coefficient measures the strength of the relationship between two variables. So, to what extent vehicle maintenance predicts or estimates fuel consumption. A value of 0 in the correlation coefficient means that the two variables have nothing to do with each other. A value of 1 indicates a perfect relationship. Knowing the value of one variable will perfectly estimate the value of the other variable. And a negative correlation coefficient between 0 and -1 would show that the two variables go in the opposite direction. An increase in one would lead to a decrease in the other one. So they go in the opposite direction. And in the same extent, correlation of 0 means that they have nothing to do with each other. Correlation of -1 says that knowing the value of one would give you a perfect estimate of the other variable, but in the opposite direction. And this correlation coefficient can be easily computed by going to data analysis, and Excel has a function or a feature that calculates that called correlation. I went to data analysis, correlation. Have to highlight the range that contains the variables. Of course, the city names are not variables. Indicate that the first column contains labels, descriptors for each one of the variables. And I'm going to put all of the results in a new worksheet. And here we have the correlation matrix. Let's make this more readable. Oh. And the correlations that matter to us right now are these ones, because this shows how fuel consumption correlate with each one of its predictors. And you can see that the correlations are quite strong. Remember, 1 is perfect correlation, -1 is perfect negative correlation. They go in the opposite direction. So knowing vehicle maintenance will give us a good sense of what is the fuel consumption in each city. Knowing the number of cars in the city also will give us a good sense of what would be the fuel consumption. Same thing for per capita income, 0.94, which is much closer to perfection than to no relationship at all. That's a correlation coefficient. Maybe we can combine the information from vehicle maintenance, number of cars, and per capita income to calculate a prediction or an estimate for the fuel consumption in each city. And that's what a linear regression does. So what a linear regression is going to do is to weight each one of the variables. Certain weight to vehicle maintenance, certain weight to number of cars, a certain weight for per capita income, mix those three variables through those weights to calculate a score, and that score would be our estimate for fuel consumption in each city. So let's pretend that we know what the weights are and build that score. I'm going to put our score over here, or our linear regression. So let's pretend we already know this. I'm going to put some numbers here. Say 1, 10, and 0.5. I'm making this up. The score is going to be this weight times vehicle maintenance, this weight times number of cars, plus this weight times per capita income, plus an intercept, something that would help us adjust the score to the dependent variable, to fuel consumption. And I'm going to put this intercept here. Okay, let's say 1. We don't know, right? So let's put a number 1 there. So what is going to be our score? If we knew those weights, we could compute the score by taking the intercept, so that's the placeholder, plus the coefficient for vehicle maintenance times the value for first city, plus the coefficient for number of cars times the number of cars in that city, plus the coefficient for per capita income times the per capita income on that city. That would give us our total score. If those were the weights, the intercept, the weight for vehicle maintenance, the weight for number of cars, the weight for per capita income, that would be our score. Now, I'm going to copy this formula down, but I want to make sure that my weights remain on the top there. So I'm going to put a placeholder on the weights. Let me copy this formula from the first city to the second city, so you see what is going on here. So the score for the second city would be equal to B1, that's where my intercept is, plus C1, which is where my coefficient for vehicle maintenance is, times C4, right? Let me put it there. So I'm multiplying C1 times C4 plus D1 times D4 plus E1 times E4 plus the intercept. That's what we have here. Now I can copy this formula all the way down because it's holding the weights to the first row. And you can see that my score is not exactly a good estimate of the vehicle fuel consumption. How do I know it's not good? I can quantify that by calculating an error. So what is the error? The error will be equal to what it should be, the actual fuel consumption, minus what my score would have predict. Oops, I'm going to put the error here. The error here is what the actual fuel consumption is, minus score. So if the value is negative, that means I overpredicted. If the value is positive, it means that I underestimated. The actual consumption is my score minus this much error. And I copy that down. That gives me the amount of error I committed in every city. So it looks like I'm overestimating fuel consumption in each city using my weights there. So by how much am I overestimating or underestimating? I can do that by taking the sum of that. Now, across all cities, I'm overestimating fuel consumption by 527 billion, right? Because every unit there is a million. I'm overestimating by 527 billion across all cities. So the problem of using the error is that if I take the sum of the error, let's do something here. I know I'm overestimating. So that instead of a weight of 1, I put a weight of 0.5 here. 1.5. You can see that the error went down substantially by almost a half. But the error has a problem, because if I have an overestimation in one city and underestimation in another city, the two errors will cancel out. and I don't want that. So if I wanted to know the real accuracy of my estimate, I should use the error square. My error squared multiplied by itself. Because now I am not going to cancel an overestimate with an underestimate. The error square will give a better sense of how far off our estimates are. Because now, okay, if I overshoot in one city and undershoot in another city, these things are not going to cancel out. It's going to say you're off. The fact that you're off by overestimating in one and off by underestimating in another city, this should not cancel out. And this is going to be our standard of fit. So the best model would produce the lowest of this number here. And by the way, none of these numbers here should have units of measurement. They're not measured in dollars. They're coefficients. And we could start playing with this. Okay, let's see here now. My total sum of squared errors is 97 millions. If I lower this number here from 1 to 0.01, it didn't make much of a difference. But if I lower this number here from 0.5 to 0.005, oh, that brought the total sum of squared errors down substantially. So the idea now, and that's the basis for linear regression, is to figure out what should be these weights here so that this particular sum of squared errors is as small as possible. This is what matters the most, the sum of squared errors. We wanted to figure out what are the intercept and the weight for each one of the predictors that produce the lowest sum of squared errors. Because the lowest sum of squared errors is the linear regression, is the score that best estimates the consumption of gasoline in each one of the cities. That's essentially how linear regression works. I created a score. And again, what is the score? The score is the intercept B1 plus coefficient for vehicle maintenance C1 times vehicle maintenance in the city plus coefficient for number of cars, which is G1, times the number of cars in that city plus coefficient for per capita income E1 times per capita income in that city. That gives us the score, and that's the linear regression. So a linear regression is a linear combination of the predictors. And our goal is to figure out what should be those weights from B1 to E1 so that we get the smallest sum of squares. And that's why the algorithm or the tool that estimates a linear regression is called ordinary least squares. But we're going to do this in a different way from what you learn in your stat or data analysis class. We're going to do this in a practical way. That's exactly what the statisticians do. They are trying to figure out what are the intercept and the regression coefficients that produce the least squares. But they do this mathematically, doing matrix inversions and stuff like that. We're going to do it by brute force. But why? Because that way we have an intuition about what is going on here. And what do I mean by brute force? We are going to use solver. Solver is a nonlinear and linear optimization algorithm. And you get solver by going to data analysis, data, solver. Of course, you have to install solver in Excel. Google it and you'll know how to do it. Solver is an integral component of Excel, but you have to install it. So I'm going to use solver. And what is solver going to do? Okay, solver is going to say, what is your objective? My objective is right here. This one. My objective is H1. And what do I wanted to do with this objective? I wanted to get the minimum. So there is maximization, minimization, and find the exact value. I wanted to minimize. In other words, I want to figure out what are the weights on B1 to E1 that would produce the smallest sum of squared errors. So my goal, my objective is the sum of squared errors, H1. And I wanted to achieve that goal, minimize sum of squares, by manipulating these cells here. So essentially I'm telling solver, find out the values for B1, C1, D1, and E1 that produce the lowest sum of squared errors. So I'm doing the ordinary least squares, right? Find the regression coefficients that produce the lowest squared errors. Now, okay, make sure that this is not checked. I think that the default in solver is that it only searches for the values for B1 and E1 that are positive. We don't want this because some of those regression coefficients could be negative. We don't want it to constrain the regression coefficients. Not in this particular case. We want a plain vanilla linear regression. So with our fake coefficients there, we got a sum of squares of about 18 million. Now let's see if solver can find a better solution than that. So I wanted to minimize H1, which is the sum of squares. I wanted to minimize by changing cells B1 to E1, this range here. And it's going to do this by brute force using what we call a steep descent search algorithm. Try to search a space of parameter values, B1, C1, D1, E1, to find what is the combination that produce the lowest value. So we are searching this valley to find what is the bottom of that four-dimensional valley. Solve. Boom. It found that the best it could do was to produce 3 million. So we went down from 20 so many millions to 3 million sum of squares. So that's our linear regression. If you want to be sure that there's no better solution than that, run solver again. Oh, you got a better result. Let's try it again. Let's try it again. Okay. Sometimes you find what we call a local optimum. So it doesn't hurt to try it. And you'd even try with multiple different values to see if this is not a local optimum. You want to find the deepest point in that four-dimensional valley. Sometimes he finds a place that he thinks is the lowest, but there is a lower point there. Now, how do we know that this is a decent solution? Should we be happy with that? We can transform this sum of squared errors into something that gives us a sense of how well matched with the actual fuel consumption. So, did our linear regression come close enough? How close our linear regression came to the actual fuel consumption? So what we're going to do is we're first going to compute the variance of the dependent variable. What is our dependent variable? Our dependent variable is fuel consumption. What is the variance of the dependent variable? We're going to use the function var. var calculates the variance. So we're going to calculate the variance. That's the variance of all the fuel consumption we observed on cells B3 to B895. That's the entire data set. What is this variance? This is the extent to which fuel consumption varies across the 894 towns that we have in our sample. That's the amount of variation in fuel consumption across cities. And we're going to compare that with the variance in the error. Not error square, but error. Same thing, var of the error. Here's the amount of variation that we got in the error. To what extent we overshot or undershot in our estimate of fuel consumption. So this is the amount of variation in the error. And comparing the error variance with the variance in the dependent variable, we get a sense of how off were our estimates. And this is done by what we call the R-square, which you probably heard about in your stat class. Is the squared correlation coefficient. What is this R-squared does? The R-square calculates the correlation between the score, our prediction, our estimate, and the actual fuel consumption. It takes a square. But it's easiest way to calculate the R-square is to say, okay, 1 minus the error variance divided by variance in the dependent variable. That's our R-square. Let me go back again. First, I calculated the variance in the dependent variable. Total amount of variation in fuel consumption across towns. Then I calculated the error variance, the total amount of variation in the error. I calculated how far above or below the actual fuel consumption our estimate, our score was, and calculated the variance for that. It says across all towns how far off our estimate was from actual fuel consumption. That's the error variance. The R square is 1 minus the error variance over the variance of the dependent variable. And what is the interpretation of that? What does that 0.98 mean? It says that we were able to explain, to correctly estimate 98% of the variance in fuel consumption. In other words, our error was only about 2%. And because what is 3,555 over 157,678 is about 2%. So our error, we were able to explain 98% of fuel consumption. And what was our linear regression? Our linear regression is 51 plus 0.93 times vehicle maintenance expenses plus 148.5 number of cars plus 0.16 per capita income. The fact that we were able to explain 98% of the variance in fuel consumption using only 3 predictors, vehicle maintenance, number of cars, and per capita income, seems quite impressive. However, we need to take other things into account before we accept those seemingly impressive results. And I wanted to talk about what we have to keep in mind when looking at the results from a linear regression. It's what I call 3 cardinal sins of linear regression. Beyond looking at R-square, we want to also to consider the dangers caused by multicollinearity. Multicollinearity happens when 2 or more predictors are correlated among themselves. If 2 predictors are correlated, essentially they share information because knowing the value of one gives you a good sense of what will be the value of the other variable if they are correlated. So essentially, if you're including these 2 correlated predictors in a linear regression, you're double dipping in information because you're using the same information twice. That's called multicollinearity, and we're going to discuss this in a few minutes. The other sin in linear regression is heteroscedasticity. If your data is quite diverse, your observations are quite diverse with a few outliers, either extremely large or extremely small values, then your regression model is going to pay more attention to some data points and less attention to others. And we're going to see how that happens. And it's easy to understand why heteroscedasticity would be a problem. Because as we saw earlier, we estimate the regression coefficients by looking at the sum of squared errors. So the squared errors grow with the square of the magnitude of the errors. So if you have a few outliers with extremely large errors, the regression is going to pay more attention to those extremely large observations, and much less attention to the extremely small observations. And the third sin of linear regression is something that we are not going to cover in this tutorial. It's called serial correlation. This happens when you are looking at longitudinal data. data that is observed over time. And also, if you're looking at spatial data, data that is geographically located, where you have to take into account the vicinity between observations. This is what we call serial correlation or spatial correlation, something that you're going to have to worry about later. Let's go back to our data that we were looking before. And if you recall, we calculated the correlations among all the variables. And we were paying attention only in these correlations, correlation between the dependent variable, fuel consumption, and the predictor, vehicle maintenance, number of cars, and per capita income. But when you ask for the correlation, you also get the correlation among the predictors. And here you can see that there is a substantial amount of correlation between each predictor, vehicle maintenance, and the other predictors, number of cars and per capita income. So vehicle maintenance has a correlation of 0.88 with number of cars and per capita income, while number of cars has a correlation of 0.83 with per capita income. So these correlations measure the extent to which those predictors, vehicle maintenance and number of cars, share information. To what extent they are redundant in information. If you include vehicle maintenance as a predictor, if you add now number of cars, you're not going to have the full benefit of an extra predictor, right? Because 0.88 of number of cars of that information is already embedded in vehicle maintenance. That's what we call multicollinearity. And what is the danger of multicollinearity? If you include two predictors that are collinear, correlated, we won't know for sure whether the coefficient that you got there is due to the predictor itself or due to the information that that predictor shares with other predictors. So as much as possible in a regression, you want to have predictors that are independent from each other. In other words, predictors that have a low correlation with the other predictors. The ideal predictor is one that is highly correlated with the dependent variable, but uncorrelated with the other predictors in your model. Let's look at number of cars. So number of cars has a correlation of 0.88 with vehicle maintenance. In other words, you cannot include number of cars and vehicle maintenance as a predictor. So how can we still consider those two predictors? A very simple trick is to do some transformation. Vehicle maintenance is the total amount spent in each city on vehicle maintenance in millions of reais, the currency in Brazil. So if I know that vehicle maintenance is highly correlated with number of cars, I can still use vehicle maintenance by transforming it into reais spent per vehicle. In other words, if I now divide this column C by D, I get a new variable called vehicle maintenance per car. How much each car, on average, how much is spent in maintenance per car. Something similar to per capita income. And that's what I have here. So I have fuel consumption, as we had before, but now I transform vehicle maintenance into reais per vehicle. So in São Caetano do Sul, people spent 647 reais per car, while in Florianópolis, people there spent 827 reais per car. While in Niterói, people spend more money in maintenance, 1,070 reais. So now we have deducted, extracted the number of cars from that variable, vehicle maintenance, because now we are using a per car, per vehicle measure. And when you do that, let's see what happens now. Now we kind of took care of substantial amount of collinearity or correlation among predictors. And notice what happened here now. On a per car, per vehicle basis, there is a negative correlation between maintenance expenses and fuel consumption. I don't know why, no idea why, but this is what the data tells us, that in a city where people spend more per vehicle in maintenance, they tend to consume less gasoline. So that's a simple way of handling collinearity. Another simple way of handling collinearity is not to include two predictors that are highly correlated. So you choose one but not both. For example, between per capita income and number of cars, I'm better off using per capita income because per capita income is slightly more correlated with the dependent variable than number of cars. But this collinearity of 0.83 between number of cars and per capita income tells me that I should not include both of them. Because if I include both of them, I won't know whether the coefficients for per capita income and the coefficient for number of cars are really due to the information contained in each one of them or is due to the shared information. We want to avoid predictors that are correlated. In order to avoid multicollinearity, our best options are to use per capita maintenance expenses and to ignore the number of cars because number of cars and per capita income are highly correlated. So our best options are to use per capita vehicle maintenance and per capita income as predictors. And this is what I have done here in my second model. And I repeated exactly the process that I described earlier on. And here are my error and error square. This is my sum of squared errors, which we minimized by using solver. I found the intercept and the two regression coefficients for vehicle maintenance per car and per capita income. And we got an R square of 0.88, which is not as good as what we had obtained earlier on with all the predictors. Earlier on, we got 0.98. However, this 0.98 is misleading because we are double counting information in this regression. We're double counting information because vehicle maintenance and number of cars are correlated and because vehicle maintenance and per capita income are correlated, and because number of cars and per capita income are also correlated. That's why by eliminating the number of cars and by replacing vehicle maintenance with a per car measurement, we lost R square from 98% of the dependent variable explained to 88%. But that loss is misleading because this 0.88, the fact that we now explain only 88% of the variance in fuel consumption, reflects the fact that we are not double counting and we have one less predictor. So with only two instead of three predictors, we now get an R square of 88%. And that's the solution for multicollinearity. Another solution for multicollinearity is to use a stepwise linear regression. Stepwise linear regression does this selection of predictors automatically. First, it looks for the very first predictor that would best explain the dependent variable. Then, given that that best predictor is in the model, look for among the other predictors available, which one would be the best to add to the regression model. That predictor is the one that is highly correlated with the dependent variable, but not correlated with the predictor already in the model. And it keeps doing it until it cannot improve the fit statistically. And to do that, it uses a statistical test called the F-test. Without getting into the nitty-gritty details on how it works, let me show you how you could do that using Kate, using my analytical tools. You go to Add-ins, Kamakura Analytical Tools, and you're going to find here Stepwise Linear Regression. Click there. It says that the add-in runs a linear regression with stepwise predictor selection. Here's some limitations in the number of observations and number of predictors. You can now highlight the data. Must have variable labels on the first row, subject IDs on the first column. Second column must have the dependent variable. already read the data. It's saying that there are 893 observations, 3 candidate for predictors. It allows you to change the default parameters for the sensitivity in variable selection and so on. I don't want to do that. So say I don't want to change. And also it allows you to do some predictive testing. To what extent the regression model that it will pick works well for making predictions out of the sample. So what it will do here, I say, let's say, reserve 30% of the sample for holdouts. And it's going to calibrate the model on a random sample of 70% of the cities that I have, and then predict the fuel consumption for the other 30% and compare the prediction with the actual data. So it makes prediction outside the sample on a holdout. There it is. It picked vehicle maintenance, number of cars, and per capita income, picked all of them, and produces an R square of 97.9%. Stepwise regression tends to be very liberal in adding predictors when you have a large sample. We have a fairly large sample of 800 and over 800 cities. So it tends to be liberal. It's very easy to pass the test because you have a lot of power in the statistical test. But that's how you would run a variable selection, stepwise predictor selection using my tools. Let's go back to our model. So this is a model that I got using per vehicle maintenance costs, expenses, and per capita income. And what I wanted to show to you is the second sin that I mentioned, heteroscedasticity. What is heteroscedasticity? So I got the best estimates that minimize sum of squares. And I got my squared error. Let's plot the squared error. Just get a bar chart of squared error. First, keep in mind that my data here is sorted by the size of the dependent variable. So São Caetano has the largest fuel consumption in millions. It's about 2.3 billion in fuel consumption. And the second largest, Florianopolis. Third is Niterói, etc., etc. So it's going in decreasing order. So the data is already sorted by the largest consumption to the lowest consumption. Let's see what happened to our errors. We're going to get a bar chart for the errors, the squared error. Here are the squared errors. And again, remember that the first observation is the largest city, the city with the highest expenditure in fuel consumption, to the smallest. And you can see here that the errors tend to be bigger. The squared errors tend to be bigger for the largest city. This is what we call heteroscedasticity. There are a few, more than a few, observations with very large values for the dependent variable. And because of that, they tend to produce large errors. And when you square them, the squared error is going to be even bigger. And because of that, when we try to minimize the sum of squares, solver is going to pay a lot more attention into those big errors. So a change in the parameters that reduces those large squared errors is going to have more consequence on the sum of squared errors. So mathematically, the algorithm solver is going to pay attention to those observations. So few observations are going to have a lot more impact on the final solution than the entire sample. And that's what we call heteroscedasticity. So what is the solution for heteroscedasticity? The most common and simplest solution is to take logs on the dependent variable. And if you have some predictors also that show disparity, okay, a few observations that are very large versus everybody else, then you do the logs also on the predictors. Here I have the data where I took log in the fuel consumption on the dependent variable, and also took log on the two predictors, vehicle maintenance and per capita income. This data is essentially the same data as in my model 2, the one that we were discussing. The only thing I did here, I took the log of column B, C, and D. And this is what we have here, the log of columns B, C, and D. And run the same regression. This is exactly the same model that we discussed, okay, we have been discussing in this tutorial. And here I have the same plot of the squared errors from the city with the largest fuel consumption all the way down to the city with the smallest fuel consumption. And you can see that there's still some heteroscedasticity. A few of the large cities have bigger squared errors, but it's not as disparate as it was before. So before I took logs, this is what we had. With the raw data, there is a tremendous disparity. The big cities have big squared errors, tend to, while the cities with smallest consumption have little error. While after taking the logs, the error is more evenly distributed. And that's the solution for heteroscedasticity. You wanted to have the observations to be in the same order of magnitude. And the way to do that, to accomplish that, a simple way to accomplish that is by taking logs. And that's our solution for heteroscedasticity. The main purpose of this tutorial was to give you a practical and intuitive sense of how linear regression works. And for that purpose, I built a linear regression model from scratch, showing you every step of the ordinary least squares estimation process. But you don't really have to do that because Excel has a function that runs regression, and you can find it under data analysis. So running a linear regression is just a matter of point and click. However, to build a good linear regression model, you want to make sure that you don't commit any of the three cardinal sins of linear regression. You want to make sure that your predictors are not correlated with each other. You want to avoid multicollinearity. And as I showed you, the simplest solution is to find some kind of transformation of the data that avoids multicollinearity. Or you can install my analytical tools for Excel because you can use it to run a stepwise linear regression. Or you can run a predictive stepwise linear regression, a selection of predictors that maximize the ability to make predictions out of the sample. The other sin is heteroscedasticity, and we found that the simplest solution for heteroscedasticity is to log transform the data. The third sin of linear regression is serial correlation that happens only when the data is longitudinal or spatial. And as I said earlier, this is something that you have to worry about later. However, if your data is spatial, so every data point is geolocated, you know the longitude and latitude of each observation, Kate can actually handle it using geographically weighted regression. That's pretty much what I had to share about linear regression.